Hi, I'm Lee Tushler with Design World and EE World, and I'm here with Dan Carnovale from Eaton, and we are standing in front of a demonstration of what you might call an energy efficiency scam. Dan, tell our viewers where we are and exactly what we have back here with this little set of capacitors wired into the line.
Okay, Lee. Hi, I'm Dan Carnovale again. We're here at the Eaton Power Systems Experience Center in Pittsburgh, and what we have here is a demonstration to show how some people are selling capacitors as energy savers. There's a lot of different types of energy savers out there that people are trying to promote, and this is just one example of them and how we can show that it doesn't quite save the energy people think they do.
Now Dan, just to be clear, all we have here, right here actually, is two capacitors that are wired across the two lines going into a motor, correct?
Correct.
And how is that supposed to save you any energy?
Well, it doesn't, but the way that it's promoted is like this. Let me show you a quick example. So we turn on this motor, and this motor, of course, is a typical half horsepower motor that would be, you know, in maybe an appliance in your home or something like that. And if you notice, it's not loaded right now. Now, what a motor needs to run is it needs reactive power to make the motor spin. Basically, it gives it the magnetic field, and it needs real kilowatts. But the only real kilowatts for a motor like this that's unloaded is basically the amount of energy that it takes to get that motor overcoming friction, which really isn't a whole lot. Now, the way that this works is when I turn on this capacitor, it also draws reactive power, a lot like the motor does, except it's equal and opposite of the motor. We call that power factor correction. So when I turn on this capacitor, it counteracts the magnetic field power that's required for this, and it compensates for it essentially from the utility side, but it really doesn't do anything for the watts.
And just to be clear, the motor electrically, it kind of looks like an inductor.
Exactly.
And the capacitor's kind of in parallel with it.
Correct. So when I take 120 volts from the line, I'm feeding one load that happens to be an inductor and another load that happens to be a capacitor. And since they're equal and opposite, what we do is we draw some power this way that's reactive power and some power this way that's reactive power, and they negate each other out from the source. But if I individually looked at each one, I would draw a certain number of amps in reactive power for this one and a certain number of amps in reactive power from this one.
Okay. And people who sell this, they have a demonstration that they purport that shows a savings in energy. Can you show us how that works?
Sure. That's the easy part with this particular demo, and this is why I set it up. Let me turn the capacitor off for a second. Okay, so what we have here is 120 volts coming in and supplying power to the motor. Now what they'll do is they'll take a meter like this and show the actual amps, not the watts, but the amps that are going to the motor. Then when they turn on the capacitor, they'll focus you in on the amps again, and what they'll do is they'll say, in our case, it went from almost 6 amps to about 3 amps. So they cut the current in half. And from a layman's standpoint, people think volts times amps equals watts, but it's really volts times amps equals volt amps.
Yep.
And that has two components. It has watts and it has reactive power, or kVAR, that supplies power to the motor. Those two make up the VA or the kVA. So when you look at the meter and you say, well, the amps went down, then you would automatically maybe assume that the watts went down. But what we can do is we can actually change this over here to watts, and we can actually see that it's roughly 155 watts right now, and when I turn the capacitor off, the watts don't change. That's the little bit of a trick that they run with.
Interesting. Now Dan, the motor's unloaded. Would this be different if it was a motor running a load?
It's a great point, Lee. So what happens is when you run the motor, a typical power factor for a motor, which is kilowatts over kVA, or watts over VA, is about 0.8. But an unloaded motor, the power factor is about 0.1, meaning there's not a lot of watts, but a lot of VA. Now, if I had a 0.8 power factor, I'd have this much watts and just a little bit more VA. So the change in current would maybe go that much instead of that much. And that's the big difference, is it's so much easier to sort of prove the point with a motor that's unloaded, even though we know that's not really the truth.
Now this is set up for kind of what you might call something that would approximate a residential system.
Sure.
But in fact, large businesses, they can get charged for a power factor that's way out of whack. Would residents ever be charged for something like that?
Now, in the U.S. right now, there's no power factor penalties. And so what a power factor penalty is again, like you said, with commercial or industrial customers, the utility bills them on a rate that's basically the kilowatts plus, if you are using a lot of reactive power, and of course a lot of industrials especially use a lot of motors, and in commercial buildings they use a lot of HVAC units and a lot of motors. So they want to make sure that their kVA capacity, which is transformer capacity, cable capacity, which is in amps, all of those things are optimized. So if a utility bills a customer that's an industrial or a commercial customer, it's because you're using up the capacity of the system. Thus the word capacitor comes in and takes some of that capacity back and gives it back to the customer, so the utility doesn't have to put a bigger transformer, for example.
Great. I understand that people who sell these actually have a couple of tricks that they kind of pull out of the box when they do so. Can you take us through a couple of those?
Yeah, there's a couple things that they do. Of course, the motor being unloaded is part of it, right? So it's easier to show on an unloaded motor. But they'll say things like, well, okay, you don't believe that I'm saving watts. Let me show you how we can save watts. And what they'll do is somewhere in their little magic suitcase box they'll have some hidden wire. And what they'll do is they'll turn on 50 feet of like 18 gauge lamp cord, maybe another 50 feet, and they'll show a watt difference from the top to the bottom. In other words, from the source coming in to where the motor is. The interesting thing of that is that's for sure actual watt losses, but they associate that with a real system, and it's so far off scale of what a real system would be is it's not appropriate. But the real losses on a typical system, let's say you had a 100 horsepower motor on a bigger system, 200 feet away from your source. You might have a voltage drop, and you might put a capacitor there, and you might have a maybe 1 or 2% savings in losses because of the I squared R losses. So here they might exaggerate that, and they might say that there's 10% losses in this wire, but of course with 18 gauge wire on a small motor like this with 5 or 6 amps running, it kind of is not comparable to what you'd see on a real system. So again, typical losses on a line like that might be 1 to 2%. So if you can only save what you lose, you can only save 1 or 2%. Their claims are typically like 8 to 25% of your power, which again is impossible.
So just so we're clear, the losses you're seeing there it's the I squared R losses, not the losses from additional inductance from that wire switched in.
No, it's exactly that. It's the resistance of the wire times the current, and if we reduce the current, because again, current and VA or kVA are proportional, so we reduce the current by putting the capacitor in. What happens is we reduce the I squared R losses. Again, it's current squared, so it does make it look like it's a big deal. But again, it's really these little tricks that they'll do, and it's unfortunate because it will make people think that it's real in their system.
Yeah. Well, Dan, all I can say is I'm certainly never going to buy one of these things.
Go ahead.
Thanks for the explanation.
Absolutely. My pleasure.